The next colligative property we're going to talk about is boiling point elevation and freezing point depression. Really, I group these together because it's the same formula that we use for both one. So a non-volatile solute, if you add that to a solution, it's going to lower the vapor pressure of the solution. This means that the solvent is going to have to be heated to a higher temperature to reach boiling. Remember, guys, boiling is when your vapor pressure of your solution equals the atmospheric pressure above the solution. So if adding a solute is going to lower that vapor pressure, then if you have a lower vapor pressure, you have to add more heat to create a higher vapor pressure to make it boil and match that atmospheric pressure. And that's why we have a boiling point elevation in the first place. Okay, so make sure you follow that train of thought. So adding a solute lowers vapor pressure. Vapor pressure must equal atmospheric pressure to come to boiling. So because vapor pressure is lowered, the temperature of boiling will be increased. Okay, so there's a formula, as always in chemistry, that will describe this. So this is our formula. So it's delta T equals I kBm. Okay, delta T is the change from your normal boiling point. Okay, not the change in temperature in general of your solution, but the change from your normal boiling point. I is the Van't Hoff factor, which sounds a lot more complicated than it is, I promise. I'll break that down in a second. It's the number of moles of ions that you get for your solute. Kb is just a constant specific to this equation, and then molality is the lowercase m. Molality, not molarity, but molality. Okay, make sure you're paying attention to that L. All right, so what does this mean? First of all, what is this Van't Hoff factor thing? The Van't Hoff factor just breaks down how many ions you're going to get from a solute. So let's pretend that our solute is Li3PO4. We are going to get a total of 4 ions from that solute because we get 3 lithiums and 1 PO4. If our solute is CaBr2, this is going to break apart into 3 ions. It's going to break apart into Ca and 2 Br minuses. CO2 is a covalent compound. It's a molecule, which means it's not going to break apart at all. So our Van't Hoff factor is just 1 here. It doesn't break apart into anything. NaBr breaks apart into 2 different ions in solution. It's ionic. And then this down here is sugar or glucose, and it is covalent. It doesn't break apart into anything, so this would give us a Van't Hoff factor as 1. Okay, so that's how you calculate the Van't Hoff factor. It's really simple. On a side note, these values over here, okay, these values sometimes will experimentally actually be lower than what we would anticipate, and that's because of something called ion pairing. So let's pretend that we have some table salt dissolved in our solution, and so if we have table salt dissolved in solution, we're going to have our NAs being pulled apart from the chlorines and attached to, or being attracted to the oxygens in our water, and likewise the chlorine is going to be attracted to the hydrogen. However, sometimes the Na and the Cl they get close to each other in the solution, they'll re-find each other, and they'll break their ties with the water, and then reform NaCl. Okay, they'll crystallize. And so where they were 2 ions, they become 1 ion. Okay? Doesn't happen very often, but if it does, that will lower the Van't Hoff factor. So experimentally, sometimes you'll get a lower Van't Hoff factor. Okay? All right, so let's apply this to a question. All right, so antifreeze contains ethylene glycol, which is C2H6O2, which is a non-volatile solute. And the question is asking us to calculate the boiling point and freezing point of a solution containing 25 grams of ethylene glycol and 75 grams of water. And it gives us the 2 constants that we would need for this equation. These are specific to water, by the way. Okay, so the first thing we're going to do is find the molality. Okay, so our molality, we're going to take our solute and turn that into grams. Remember, guys, molality is moles of solute over kilograms of solvent. So we're going to turn this first into moles and then divide. So we have our moles of solute over kilograms of solvent, and all I did was just take 75 grams and put that into kilograms, okay, of water. And we get our molality of the solution. And then we plug it in. That's the next step. We plug into our formula. So here is our formula, delta T, I, KBM. The Van Hoff factor. So ethylene glycol, if you guys take a look at it, is a covalent compound. So if it's covalent, it's going to have one little particle floating around. It doesn't separate into ions, so our Van Hoff factor will be 1. This is the Kb. It's a constant. It's constant for water. This never changes if water is the solvent. So Kb, this was just given to us in the problem. And then the molality we calculated just 4 seconds ago is 2.6 molality. Okay, so crunching all that together, we have our change in boiling temperature is 1.33 degrees Celsius. So this means then that we're going to apply it. That's our next step. So the initial boiling temperature of water is 100 degrees Celsius. So we're applying our change, so we're going to add that 1.33 degrees Celsius, and our new boiling point is 101.33 degrees Celsius. That's our new boiling point. Okay, so just remember, if you're calculating boiling point, you are adding to the initial or the original boiling point of your solution. Okay, to find the new one. So that's boiling point elevation. So while the boiling point is raised, freezing point is lowered. Okay, so boiling point elevation, freezing point depression. So to find the freezing point, it's literally the exact same equation, except the constant is Kf instead of Kb. So the change in the freezing point is equal to the Van Hoff factor times the Kf times the molality. Okay, so let's continue this example then. We're going to plug into our equation. So our change in freezing point is the Van Hoff factor, which was 1 in the question, times the Kf, and this was given to us in the problem. Okay, this is our Kf for water, times the molality that we already found, and so we find that the change in the freezing point is going to be 4.836 degrees Celsius. Okay, so now we apply it. Okay, so when we apply it, with the original freezing point of water is 0, and now we apply this change in temperature, and because it's freezing point depression, we lower it, so we subtract. Okay, we subtract from our original freezing point, and we get negative 4.836 degrees Celsius is the new freezing point of our solution. Okay, so that is the second, and honestly, almost done with colligative properties. We only have one more, and we'll cover that tomorrow.